Hello guys, my name is IBM. Today I'm going to record Physics 9702. This is going to be paper 5. A friend of mine in Pakistan told me to record 9702 paper 5 too because he wants to get a clear picture of what is really required from paper 5. So my friends in Pakistan, thank you for being the biggest community that shares my videos, and I wish you all the best. Without wasting time, I would like to take you to the question paper, paper 5-2, planning, analysis, and evaluation. So I'm trying to solve this to give you a picture of what really the examiner would be looking for. So without wasting time, I'll take you to the question paper, which is here. So this is paper 5. It is called Planning, Analysis, and Evaluation. It's October, November 2023. This is 970252. The paper is always 1 hour and 15 minutes. So it means you should be able to divide your time into two parts. 45 minutes for question number 1 and 45 minutes for question number 2. So you must answer all questions. I think you're familiar with all these instructions. The total mark for this paper is 30. This paper is very important for those who are doing A-level exams. This paper is very, very important. So you need only 20, you need to get at least 18 out of 30 to be able to maintain an A star if you're aiming at an A star. So question number 1, two identical beakers, each of mass m, are attached to each other using a thin and using string and suspended from a pulley as shown in the figure. So this is the diagram. We have two beakers. Okay, the beakers are held at rest at a height h. So first of all, you're now thinking about how you're going to measure h. So you'll measure h using maybe a meter ruler, which must be clamped. Okay, cooking oil of volume V is added to one of the beakers. So you're going to add cooking oil in one of the beakers. So in your diagram, you are thinking that you must add cooking oil in one of the beakers. So you label this as oil. Cooking oil of volume V. So to measure volume, you know that you must know, to be able to know the volume of the oil, you must be able to use a measuring cylinder. So here you are planning, you are trying to think about how your experiment is going to be done. So this is, you need the measuring cylinder to measure this volume. Is added to one of the beakers. So one of the beakers, we have added the volume V of oil. The beakers are raised so that the beaker with the oil begins to fall. The speed of the beaker as it reaches the surface is z. So to measure speed, you need the distance, you will need the distance and time. So that means you will need a stopwatch or you may need light gates. But for this experiment, I will just use a stopwatch. When I use a stopwatch, I must repeat measurements to get an average value of z. So here I will just say I will need a stopwatch to measure t. Okay, so far, if I have this in mind, so far I have already almost 5 marks. If I know that I'll use a stopwatch, measuring cylinder, a ruler which is clamped, I'm labeling oil, I have about 5 marks before even I start writing. I know in my mind I am making 5, I'm scoring 5 marks already out of 15. It is suggested that Z is related to V by the relation 2h over Z squared is equal to 2m over ABV plus 1 over B, where A and B are constants. Plan a laboratory experiment to test the relationship between Z and V. So first of all, we have to choose which one is the dependent variable and which one is the independent variable. The independent variable is the one you change as the experimenter. For example, Z only changes if V has been changed. So it means V is the one which you are going to change as the experimenter. So V is going to be called the independent variable and Z is going to be the dependent variable. So if I can identify the independent and dependent variable, then I will be able to get another mark. Then which quantities in the experiment, if not kept constant, will affect the results? Number 1, I must make sure h does not change. So I must release the beakers or is from the same height. So h must be kept constant. H must be kept constant. So if I identify h to be kept constant, I now will get a mark for that. Which other quantity, if it changes, affects the results? It must be the mass m of the beakers. The mass m of the beakers should remain the same. If a beaker falls and some part of it breaks off, it means the total weight of the beaker and its contents has changed. So the mass m of the beaker should remain constant. M should remain constant. That is also another mark. But how will I measure M and ensure that it's always constant? I must use a top band a balance. So I will say use a top band balance to measure M. So this is another mark. I have not started writing, but I'm now coming up by just reading through the question. I'm trying to come up with things that I know would give me marks by just looking through the question. Then draw a diagram showing your arrangement. So I will have to draw a diagram. For example, I know that the pulleys cannot be hung in space, so I must put them on. I now will put the pulleys on a stand. I will need a stand for the pulleys. I must clamp the pulleys. I must have a ruler to measure h, so I will also clamp the ruler somewhere. But the ruler is vertical. How will I ensure that the ruler is vertical? I may either put a set square somewhere, or I may use a spirit level. A spirit level will help you to know that the ruler is vertical. So either you'll use a set square placed beside the ruler to ensure that it is vertical because you want to measure a height h. And how will you ensure that you release h remains constant? You must put a reference mark. I can put a reference mark on the ruler. Okay. So my diagram will somehow look like this. But remember, when the oil falls, when the container hits the surface, the oil may go out. So how will I prevent the oil from going out? I may need to add a lid. I may need to add a lid on this container. So I may need to add a lid on the container. And also I may need to add a cushion or a sand tray at the bottom here where I may need to add a cushion here at the bottom where the cylinder may hit this, instead of hitting the surface or the table, it may just hit the cushion here. It may just fall on the cushion so that it doesn't deform, doesn't break. So this is a cushion, or it could be a sand tray. So all these ones would give you marks. So what I'm remaining with here is now analysis. Draw a diagram showing the arrangement. I now have a picture of how the diagram would look like. Explain how the results could be used to determine values for A and B. Now this is the analysis part. So for analysis, which graph am I going to plot? So we normally plot a graph of, we normally put the independent variable or something related to the independent variable on the x-axis, and we put a dependent variable on the y-axis or something related to the dependent variable. So when I look at the equation 2h over z squared equaling to 2m over a b v plus 1 over b. I want to make the independent variable to stand alone, or the dependent variable to stand alone. The dependent variable is z. So I'm going to take 2h the other side. So when I divide both sides by 2h, I remain with 1 over z squared on the left is equal to 2m over 2h a b times 1 over v. Because I know v is the dependent variable, I try to separate it from this quantity here. Then plus 1 over, remember I divided everything by 2h. So this is 1 over 2h times b. So which graph am I going to plot? The easiest graph to plot is if I compare with the y equals to mx plus c. On the y-axis, I will plot 1 over z squared. On the x-axis, I can plot 1 over v. So it means the gradient is going to be equal to that. The y-intercept will be equal to that. So I will plot a graph of 1 over z squared against 1 over v. And that means the gradient The gradient is going to be 2m over that, which is m over ABH, and the y-intercept is going to be equal to 1 over 2BH. So when I have this analysis, then I think I'm good enough to go. So any safety precautions? Of course, by putting a cushion here, I have taken safety precautions. Because oil in contact with the skin may have an effect, I may need gloves to prevent the skin from coming in contact with the oil. Okay, so now let me go to, I've finished to come up with a sketch in my mind of how my experiment will be carried out. So now I'm going to the real page to start doing the experiment. So I'm going to start by drawing a diagram. Let me start by putting a surface here. Okay, let this be the bench. Or let this be the bench, or it can be the table. Okay, so I need a clamp to hold the cylinders. Okay, so this is going to be my stand. So I need to hold the pulley. So I'll put the pulley somewhere here. I'm trying to draw something good, but you can draw something better. I just want to show that I'm very good at art. Just want to show that this is a pulley which is being held here. If you have a pencil, you can draw something better. So I will now put the cylinders. I'll put a string. to hold the cylinder on one side. Then I'll put another cylinder the other side. So I'll show that I'll put a stopper or a lid. Then in here I should put oil. And this should be of course on the same level, so I'll put a horizontal line down here. These cylinders are supposed to be identical. It's hard for me to make them perfectly identical, but for you, if you're drawing on a paper, you can make them perfectly identical. So I must ensure that the height of the cylinders above the surface where the cylinder is going to fall is h. So this height is going to be h. So I first put here cushion. I want the cushion to be the same height as the base of the stand. So this is the cushion. So you can shade it to whatever way you want, but this is the cushion. So I said instead of a cushion, you can put there a sand tray. Okay, so to measure the height h, I need the height h, which is going to be measured using a ruler. So let me make this base longer. So I'm going to put here a ruler which I'm going to clamp. So this, to show that this is a ruler, I could put marks. But of course, those marks are not enough to show that this is a ruler. So I must mention that this is a rule or meter ruler, wherever you want. I can say it is a meter ruler, a meter rule. So this is the string. This is the city. Here we have oil. This is the lid or stopper. And you can label the cylinder because labeling is very important. Of course, I must attach a pointer here so that I maintain h at the same level. So I'm using tape. So this is a pointer. To make sure that I always release the cylinders from the same level, that is going to be a pointer. So I've attached tape. Then this ruler is not standing on its own, so I must clamp it. So to clamp this ruler, I'll attach a clamp here. So this is of course the stand. These are clamps. Okay. Now to also ensure that the ruler is vertical, I must use either a spirit level or a set square. So I'll use a set square. Maybe I should change the color here, since this is just, I want to attach a set square so that is visible. Of course, you have to draw a nice diagram. That's why I'm trying my level best to use a ruler. So I'll put a large set square here besides the ruler. So this is not enough to show that this is a set square. So I have to label that this is a what? A set square. Yeah, I think I've exhausted everything that I need for this diagram. I think this diagram has almost, um, if the examiner was to mark only the diagram, because some information may be repeated in the essay, or some information may be credited in the diagram and not credited in the essay because it would be a repetition. But this diagram shows almost more than 5 marks. Putting a cushion here could be a mark. Ensuring that the ruler is vertical could be a mark. Ensuring that the height h is going to be constant, or how you are going to ensure that you release the cylinders from the same height using a pointer, that is a mark. You have oil labeled, you have labeled oil, meter, ruler, stand, and so on and so forth, that is a mark. You have clamped, you have support for the cylinders, that is a mark. You know, this is almost 1, 2, 3, 4, 5. About 5 to 6 marks here without even writing anything. So let's now write the essay. So in this experiment, I have to identify the dependent and independent. In this experiment, we have already said that V is the independent variable. And Z is the dependent variable. So V is the independent variable and Z is the dependent variable. So this is automatically a mark. That is automatically a mark. Alternatively, you could say I will vary, in this experiment, I will vary V and measure Z. Alternatively, you could say, instead of saying V is the independent variable and Z is the dependent variable, we would simply say I will vary V, because we always vary the independent variable. I will vary V and measure Z. It is the same thing, you don't need to repeat yourself. Okay. Then of course you must mention what you should keep constant. So I will keep H constant. You don't say H is the control variable. No. You must say I'll keep H constant. Yes, it is true, it is the control variable, so it must be kept constant. You say I'll keep H constant. And how will you ensure that H is constant? I've also demonstrated that in the diagram. But you can still write it here. I'll keep H constant by ensuring the beaker or the beakers are always released from the same point determined on the clamped rule. So I will keep H constant by ensuring the beakers are always released from the same point determined on the clamped ruler. So that point I've attached a pointer. My pointer is here, where I will always be releasing the cylinders from. I've attached a pointer here, where I will be always releasing the cylinders from. Okay. So when I mention that, it means I qualify for another mark. Okay. But when you just say H is the control variable, you will not get the mark. You can't get that mark. So that is the introduction part. To collect and analyze data, I'm now into the essay to collect and analyze data. I will take the following steps. So which steps will you take? If you want, you can number them. Let me say step number 1. First of all, I will measure the mass, because I said I need to measure the mass of the cylinders and ensure that it is always constant. So I will measure M, which was the mass of the cylinders. I will measure the mass M of the beakers. And which instrument will you use? You will use a top pan balance. So using a top pan balance. You need to use a balance to measure the mass, not a weighing scale. You must be very specific. Using a top pan balance, and ensure that M remains constant throughout. If M changes, the experiment will have changed. It means the total weight of the beakers with its contents have changed. So you must always check M with your top pan balance to ensure that it has not changed. So if I mention that I will measure M using a balance, that is a mark. And if I mention that I must ensure that M is remaining constant, that is another mark. So before I write mark, you notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9 marks out of 15. Okay, so it's always good to write as much as you can so that the examiner will look for at least 15 marking points. So for your task should be just to write as much as you can, write the details of your experiment. So step number 2, I'll now build my experimental setup as shown in the diagram. I will build the experimental setup as shown in the figure above. So now since now you know the mass of the cylinders, you can now assemble your apparatus as shown in this diagram. Okay. Step number 3. Remember you had to ensure that the ruler is vertical. The mark has already been given in the diagram because you have put a set square, but you can still write it here. I will ensure that the roll is vertically clamped. By placing a set square besides the ruler as shown in the diagram. So I have ensured that the ruler is vertical by placing a set square besides the ruler as shown in my diagram. That's why I've put this set square. But I said you could, instead of putting a set square, you should be able to use a spirit level, which builders use to ensure that something is flat, something is horizontal or vertical. So you could use, besides that, you could use a spirit level. So I'm not putting ticks here because this one will not, saying I will build the experimental setup as shown in the diagram will not give you a tick. You have already shown that in the diagram. I will ensure that the rule is vertical. I've already credited it in the diagram because where there is a set square, I put a B1 here. So there is no need of, you can't be credited twice for the same implication. Then next, step number 4. Remember, I have to now measure and record H. So step number 4, let me measure and record H. So step number 4, I will then measure I'll then measure H. I will then measure H, of course, from the ruler, ensuring that H is large enough. Of course, you must ensure that the height H is big enough. If it is very short, if it's a short distance to the surface, it means before you press start, the cylinder will have hit the cushion, or it will have hit the surface. But if H is big enough, then you have more time to record. You have more time to record before the cylinder hits the surface. So H should be large enough to reduce the percentage uncertainty in the time. So I'll then measure H I will then measure H, of course, from the ruler. I can't be credited again for measuring H using a ruler because I've already been credited for the ruler in the diagram. But I will be credited for ensuring that H is large enough so that the time of fall of the beaker is measurable with a small percentage uncertainty. Is measurable with smaller percentage uncertainty. If the height is bigger, it means the cylinder will take more time to hit the ground. Whenever we measure a large value of a quantity, we have a smaller percentage uncertainty. If H was smaller, the time would be too short. That would give a large percentage uncertainty. So this point here would give me a B1 mark, knowing that H should be large enough. That would give me a bonus 1 mark. Then step number 5, I want to try and keep time. Step number 5, I haven't measured the volume, so I will measure the volume. I will measure a volume V of oil. And what will you use? You will use a measuring cylinder. So using a measuring cylinder, and then transfer it into one of the beakers, and then transfer it into one of the beakers. So 5 could come before 4, there's no problem with that. You would first measure V, then you measure H, and so on and so forth, but the order doesn't matter. So I'll measure volume V of oil using a measuring cylinder and then transfer it into one of the beakers. Okay, so that is automatically V1 mark. Then 6. I'll now release the beakers from height H, which I've already measured. I will now release the beaker or the beakers from a height H and immediately start the stopwatch. To measure the time t of fall of the beaker. To measure time t of fall of the beaker. So I will have, of course, if you don't want to use a stopwatch, I said you can use light gates, but the light gates must be connected to a timer or they must be connected to a data logger. So to avoid that, I'll use a stopwatch, but if I use a stopwatch, I must repeat the measurement. Now the question is, how will I determine Z? Can I say Z is H over T? Not at all. Let's see how will I determine Z. So if we assume acceleration due to gravity is constant, then I can use equations of motion. I can say V equals to U plus AT. This is now speed. V equals to U plus AT. If A is constant, we are releasing, so U is 0. So it means V is going to be equal to G, or acceleration, times T if U is equal to 0. Then if I also use S is equal to UT plus a half AT squared, remember U was 0, so S is H. The cylinder is falling through a height H. So H is equal to a half times the acceleration times T, but it is squared. Remember V was Z, this was Z, because Z was, no, V is, yes, V was Z. So it means Z is equal to AT, but we don't want AT, we don't want acceleration in our equation. So if V which is equal to 8 is the same as Z, then I have to combine V which is equal to 80 with Z equal to Z with H equals to half AT squared. So I'm going to remove A in the expression. So AT alone is Z. So it means H is a half times AT times T. AT alone is Z. So it means H is equal to a half times Z times T, which means Z is going to be equal to twice H over T. So using equations of motion, I know that now z will be equal to twice h over t. Twice h over t, that is the speed with which the cylinder hits the ground. We're not looking for, because the speed is not constant. The speed is not constant, so I can't say h over t, not at all. The speed goes in increasing because there's an acceleration. That's why it is wrong to say z is equal to h over t. So step number 7, I will determine z. I will determine z from z equals to twice h divided by t. So I'm saying z is not equal to h over t because z is the speed with which it hits the ground. And remember, if the acceleration is constant, the speed goes on increasing at a uniform rate. So z is 2h over t. Okay, so I already have 2 marks. I can indicate them here. No, this will, of course, this one of releasing. I have a mark for the stopwatch. That is 1 mark. And for measuring h, that is another mark. Okay. So for determining z from a correct expression 2h over t, that is another mark. So step number 8. I'll repeat measurements. So I will have to repeat now measurements because remember, when you are measuring time using a stopwatch, you must repeat measurements and take the average. So I'll repeat measurements. Or I'll repeat, I think I should repeat step 6. I will repeat measurements no, I'll repeat step 6 and 7 for the same value of V. I will repeat steps 6 and 7 for the same value of V. And obtain the average value of V. I mean the average value of Z. So if I repeat and obtain the average value of Z, of course I must be credited for that. Okay, so all along I have been recording data for just one attempt. So I have now to get 6 sets of results. So I'll repeat steps. Which steps should I repeat here? I think I should repeat from step 5 to 8. Okay. So I will repeat steps 5 to 8 for different values of V until I have at least 6 sets of results. Until I have 6 sets of results. Okay. So if I have 6 sets of results, now analysis comes into play. That is now step number 10. I will now plot a graph. We have already known which graph I will plot. So I will plot a graph of 1 over z squared against 1 over v. But which graph should this be? So if it is a straight line, of course it is not passing through the origin because it has an intercept which was 1 over 2bh. So if it is a straight line, passing through it passes through 1 over 2bh, that is the y-intercept, then the relationship is valid. The relationship is valid. So we are still on analysis. What is the gradient going to be? We know that we have already seen that the gradient was equal to, was it m over abh? That the gradient was m over abh and the y-intercept was 1 over 2bh. So we're now on analysis. So the gradient is equal to m over abh. Because they wanted us to find a, you just tell the examiner that this implies that a is going to be equal to m divided by the gradient times bh. And the y-intercept, of course, for the y-intercept, you tell the examiner that the y-intercept was equal to 1 over 2bh, which implies that b is equal to 1 divided by, I think that is twice h times the y-intercept. Okay, that is analysis. Then for safety, so let this be step number 11. I'll tell the examiner that for safety, what will I do? So for example, one of the safety measures, I've already indicated them in the diagram, but I would say I would use gloves to avoid the skin getting in contact with the oil. I would use gloves to avoid the skin getting in contact with the oil, because oil could have an effect on the skin. The other one could be, I've already indicated it in the diagram, but I can still write it here. I will use a cushion, or you could say sand tray, for falling beaker to land. For the falling beaker to land. And I've also placed a lid to avoid oil spillage. Okay, so I have already more than enough marks, because the examiner will look for 15 marking points in your essay. This one of repeating steps will not give you an extra mark, but this one of plotting, that is 1 mark. If it is a straight line, that is the analysis of the graph, that is a mark. Answering A equals to that, that is a mark. B equals to that, that is a mark. Safety, that is another mark. So the examiner will look for at least 15 marking points to give you 15 marks. 15 marking points, 15 marks. So you can always write as much as possible for this experiment. Okay, so that is question number 1. I went past time because I was trying to show you, to give you details. Let's try question number 2. Normally, question number 2 is very easy. If a student knows the rules of uncertainties, combination of uncertainties, the student will take short time to on question number 2. The student investigates the discharge of capacitors in the circuit as shown in the figure. So these are the capacitors. The capacitors have capacitance CA and CB, and you see that they're in series. Capacitors in series are obtained from product over the sum. The student closes the switch to change the capacitors. To charge the capacitors. The switch is opened and a stopwatch is started. The capacitors discharge through the resistors, the resistor of the resistance R. At a fixed time t, the voltmeter reading V is recorded. The experiment is repeated for different values of CA and CB. For each value of CA and CB, the combined capacitance is calculated. It is suggested that C and V are related by the equation. We have seen this equation in capacitance. This is the discharge of a capacitor where this I naught R is supposed to be V naught. V naught is I naught times R. A graph is plotted of ln of V on the y-axis against 1 over C. So I have to make ln of V the subject. So I'm going to introduce ln on both sides. So on the left hand side I have ln of V equals to the right hand side I have ln of I'll have ln of I naught R plus ln of e power minus t over CR. So this means my equation becomes ln of V equals to ln of I naught R plus. When I get ln of E, I only remain with the power. So this would be negative t over CR. I'm rearranging the equation, so it will be ln of V equaling to negative t over C over R times 1 over C. I just broke down this negative t over CR into two parts. Then plus ln of I naught R. If I try to compare this with y equals to mx plus c, it means on the y-axis, I have ln of V. On the x-axis, I have 1 over c. So it means the gradient is minus t over r. So the gradient is going to be minus t over r. And the y-intercept is ln of I naught r. So this is ln of I naught times r. That is 1 mark. Values of CA, CB, and V are given in the table. The relationship between CA and CB is 1 over C equals CA plus CB over CA, CB. Calculate and record values of 1 over C, 10 to the power 4 farad, and ln of V in the table. Include absolute uncertainties for ln of V. Okay, so let's first calculate 1 over C. You must make sure that you at least maintain the same number of significant figures. You see that these are 2. So we must maintain 2 significant figures. So the formula is CA plus CB over CA times CB. Okay, so I will not consider the power of 10 because I know if I don't consider the power of 10, here in the numerator I have times 10 to the power of minus 4, and here I have times 10 to the power of minus 4 times 10 to the power of minus 4. So one of these cancels the one in the denominator, and when it goes up, it becomes 10 to the power of 4 when it goes up. So I will not consider the power of 10. I'll just consider the values in the table. So I'll say 2 point, let me open the bracket, 2.2 plus 2.2 divided by 2.2 times 2.2. So this is 0.9090, so it becomes 0.91. To two significant figures, it is 0.90 recurring, so it is 0.9090 and so on. So two significant figures to be 0.91. I could record 0.909, but when you have many significant figures, of course, plotting becomes the challenge. The second one, 2.2 times 2.2 divided by 2.2 times 3.3 divided by 2.2. Let me repeat this. Open the brackets. 2.2 plus 3.3 divided by, open another bracket, 2.2 times 3.3. So this is 0.757575, so it becomes 0.76. Okay. The next one is 2.2 plus 5.6 divided by, open brackets, 2.2 times 5.6. So that is 0.63. So two significant figures will be 0.63. The next one is 3.3 times, plus 3.3 divided by 3.3 plus, so this is times 3.3, which gives us 0.606060. So to one significant figure it is 0.61. Because it is the 60 recurring, 0.6060 and so on and so forth. So it becomes 0.61. Then the next one is 3.3 plus 5.6 divided by, open brackets, 3.3 times 5.6. So that is 0.48. The next one is 5.6 plus 5.6 divided by 5.6 times 5.6. So that is 0.36. Okay, so that is the column for 1 over c. Then ln of v. I'll first find ln of v. Of course, the rule for ln or logarithm, natural log or logarithm, the number of significant figures becomes the number of decimal places when I take the ln or the log, whichever it is, whether it is log or ln. The number of significant figures becomes the number of decimal places. For example, it becomes the number of decimal places or more. You can increase the number of decimal places, but you cannot reduce. So I can say ln of 2.45. Those are three significant figures, so I'll call the answer to 2 to 3 decimal places or more than 2. I mean, or more than 3, but I'll just record 3. So this gives us 0.896. So this is 0.896 to be plus or minus. So ln of 2.75, it is 1.012, 1.012 plus or minus. So here I have written there are 3 decimal places. Then I find ln of 3.05. It's 1.115 plus or minus. Let's check ln of 3.10. That's 1.131. 1.131. 131 plus or minus. Let's check ln of 3.50. That's 1.253. 1.253 plus or minus. Please make sure you round off mathematically correctly. Okay. Then I'll have ln of 3.85. That's 1.348. 1.348 plus or minus. Okay, now let's find the uncertainties because the question says include the uncertainties in ln of v. So to find the uncertainties in ln or any log, you can get ln of v minus ln of v minimum. What do I mean by that? For example, I'll say ln of 2.45 minus ln of the minimum value of v is going to be 2.45 plus, minus, because it is minimum. It is minus the uncertainty, which is 0.05. That will give you the ln. Or you can get ln of v maximum minus ln of v. That is, ln of v maximum will be 2.45 plus 0.05. That is the maximum value of v minus ln of v exact, which is ln of 2.45. Or you can get the ln of v minimum, v maximum, minus the ln of v minimum divided by 2, but that is a wastage of time. You can say ln of 2.45 plus 0.05 minus ln of 2.45 minus 0.05 and divide this by 2. So you have three methods, 1, 2, 3. You can choose one, but I'll just take this one here, ln of v exact minus ln of v minimum. Okay, so I will say ln of 2.45, that is exact, minus ln of 2.45 minus 0.05. That is the minimum value of v. So which gives me 0.0202. I may maintain the same rule of number of decimal places of the so that the number of decimal places of the uncertainty is the same as the number of decimal places of the value of ln, or I can maintain one significant figure, so whichever. So I may record this as 0.02, maybe 21, whichever. I can record 21, but I could still record 0.202. One significant figure is fine. After all plotting, we are going to round off to one significant figure for the error bars. Then the next one is going to be ln of 2.75 minus ln of 2.75 minus 0.05. So that is 0.018. 0.018. The next one is ln of 3.05 minus ln of 3.05 minus 0.05. So that is 0.016. It's actually 0.017. 0.017. The next one is ln of 3.10 minus ln of 3.10 minus 0.05. So that is 0.016. 0.016. The next one is ln of 3.50 minus ln of 3.50 0.50 minus 0.05, which gives me 0.014. 0.014. And the last one is ln of 3.85 minus ln of 3.85 minus 0.05. So that is 0.013. Okay, so those are the uncertainties in ln of v. So it is plus or minus. When any method you use, the answer is going to be approximately the same. Approximately the same. They may vary slightly in the last digit, but they're approximately the same. Then plot a graph of ln of v against 1 over c. Include error bars for ln of v. So let's go to plot the graph. Okay. So our first point is 0.91 on the x-axis. No, it is 0.896 on the x-axis. Sorry, on the y-axis, and 0.91 on the x-axis. So let me first look for 0.91. I must know the scale. I must know the scale on the x-axis. So on the scale on the x-axis is 0.4 minus 0.3, that is 0.1 divided by 10. So on the x, each box is 0.01. Then on the y, each box is 0.95, 90 minus 0.85 divided by 10 boxes. On the y, each box is 0.005, each small box. Okay, so I want to plot 0.91. The first point is 0.91. On the x, it is 0.91. On the y, it is 0.896. 0.896. So 0.91, because each box is 0.01, so 0.91 is going to be here. Then 0.896, so I have to check. I'm plotting 0.896 starting from 0.850. So how many boxes are these? I'm dividing this by the scale on the vertical, which is 0.005. So I must add approximately 9 boxes from 0.85. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this should be here, approximately here. Okay. The next point is on the x-axis is 0.76. On the y-axis is 1.012. So 0.76. So this is 1, 2, 3, 4, 5, 6 against 1.012. So to plot 1.012, I know it is after 1, so I'll say 1.012 minus 1 divided by the scale on the vertical, which is 0.005. So how many boxes are these from 1? Those are 2, approximately 2.5. So approximately 2.5. So 1, 2, it is approximately here. Approximately in the center, it is very close to 2.5 boxes. So it's approximately in the center here. Okay. Then the next one is Next one 0.63 against 1.115. 0.63, so 1, 2, 3. 0.63 is here against 1.15, so 1.115. I think this is after 1.1. So 1.15 minus 1.1 divided by the scale, which is 0.005. So I'll add 3 boxes from 1.1. So 0.63. So 3 boxes, 1, 2, 3. So it is exactly here. That is the point. Okay. Yes, very good. The next one is 0.61 against 1.31. 0.61, 0.61, just one box, against 1.131. So I'll check with my calculator. From 1.3, how many boxes are those? 1.131 minus, no, it is after 1.10, minus 1.10 divided by 0.005. Those are 6 and approximately 6 boxes. 6 boxes from 1.1. So 6 boxes from 1.1. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is going to be the point. Then the next one is 0.48 against 1.253. 0.48. 0.48, this is 41443445464748 against 1.253. 1.253. So how many boxes are those? 253. If you want, you can check with your calculator. 1.253 minus 1.25 divided by the scale, which is 0.005. Those are approximately half a box. From 1.25, I'll add approximately half a box. So approximately just half a box. So I'll just plot this point around here. Okay. And the last one is 0.36 against 1.348. 36, I just add 6 on the x-axis. Then 0.3848. I'll check with my calculator. 1.348 minus 1.3 divided by the scale, which is 0.005. Those are approximately 10 boxes. So, or approximately 9.5. So 3.6, 0.36. Then the other point is very close here, almost here. Okay, so that is the approximate point. And now the next thing is to draw the line of best fit and draw the error bars. So for the line of best fit, I'm going to fit this on the same page so that, because there's no way I can sketch this, balance the points if it is not on the same page. Okay, so I'll try my level best to do a better line of best fit. Remember the principles, you balance the points. You should balance the points. Please remember to plot with a pencil so that when you have a mistake, you can always rub off. Do not plot with a pen because if you make a mistake, it becomes weird. It becomes bad and terrible. So me, I'm plotting with a pen, but you should be plotting with a pencil. So let me try to draw the line of best fit. And I see if it is very possible. Remember, I'm drawing on a computer. You should be able to draw a better line than mine. This is not good enough. No. Let me make another attempt. Please remember to draw a better line of best fit than mine because mine is on the computer, so it cannot be very accurate. Do not aim at joining the first and last point. That is wrong. Just aim at balancing the points to ensure that the line cannot be rotated any further. Well, still I don't believe this line. I still don't believe this line unless I plotted wrongly. But I'm sure I plotted correctly. Okay, let me try to check one of the points, which is 0.63 against 1.131. I mean 1.115. I have to check that again. 0.63 against 1.115. So 1.115 minus 1.1 divided by 0.005. Those are 3. And I counted 3. The other one was 0.61. It was against 1.131. 1.131 minus 1.1 divided by 0.005. Those are 6.5. 6.2. And I counted 6. So it means the plotting is fine. But the line of best fit is not good because the points are not balanced. Okay, let me try my last attempt. If I fail, I'll leave it for you as an assignment to draw a better line of best fit. Okay, I think this is the best I can try. I'm trying my level best to balance the points. So this is 1 point, this is the second one. I can say this is on the line, the third one is approximate on the line. Okay, that is enough line of best fit for me. You can draw a better one. But of course, when I expand this, you notice that the line may be very far from the points. So, and I can't draw this I can't draw this and just extend it downwards. It doesn't really make good sense. I have to put the line once to ensure that the points are balanced. So I'll just use this line. You can draw a better line of best fit. So using this line, which I've just drawn, so I will label this line of best fit. This is line of best fit or best fit line. So the next thing I have to do is to do the error bars. The error bars are for ln of v, which is vertical, so the error bars themselves are also going to be vertical. The first error bar is 0.021. I think it was 0.021, 0.018, 16, 14, 13. I remember them. So the first error bar was 0.021. If I want to check with the scale, 0.021 divided by the scale 0.005. How many squares are those? Those are 4 upwards, 4 downwards. So I'll count 4 upwards, 4 downwards from the point. So 1, 2, 3, 4. This is approximately here. I need to use a thicker line for the error bars. They look more beautiful when they are thicker. So use a ruler to draw very neat error bars. So I'll count 4 upwards, 1, 2, 3, 4. Approximately 4 because it's 4.2 squares. Then I'll join this with the ruler. Beautiful. The second error bar was 0.18. I can check with the scale. 0.018 divided by 0.005. Those are 3.5, approximately 3.5 squares up and 3.5 squares down. So this was in the middle of the box. So I'll say 1, 2, 3. I can stop at 3 because it's almost in the box here. So this is going to be approximately here. And 1, 2, 3. It is slightly at that point, approximately 3.5 squares because the point was already in the center. So 3.5 squares will stop at the third square. No, the one at the bottom is not correct. One, two, three. This should be somewhere here, not at this point here. So the error bars look so beautiful when you make them thick and use a ruler to draw them. They look so beautiful. Then the next one I think was 0.016. So I'll just check my calculator. 0.016 divided by 0.005. Those are 3 upwards, 3 downwards, 3 and approximately 3.2. So you can put 3 up, 3 down. So this was at that center, 1, 2, 3. So this will be here. Then 1, 2, 3. So this should be here. So then a vertical line. The next one was also 0.16. So 3 up, 3 down. 1, 2, 3. 1, 2, 3. The next one, I think it was 0.14. I can check with my calculator. 0.014 divided by 0.005. Those are approximately three small boxes, approximately three boxes. So, and this was in the center. So 1, 2.5. So it is going to be approximately here. This is a half, 1, 2. This is going to be approximately here. Because it is in the middle of the box, so I know it is 2.5. So that's why I'm just moving slightly beyond the line. Okay, you may not need to make it very, very thick like I'm doing, but I'm saying you can just pass there the pencil like 2 times or 3 times to make it a little bit thicker. The last one was 0.013. 0.013 divided by 0.005. Those are approximately 2.5 boxes. But since the point we plotted was almost in the center, so I'll just add 2 boxes. 1, 2. 2 down and 1, 2. 1, 2 and 2 up. So that is approximate. Okay. The next thing is I'm going to now draw the line of worst fit. You can choose to draw a steeper line or a shallower line. The only way I can draw a reasonable line of best fit is by fitting this on the same page. If I don't fit it on the same page, then the judgment of the points will be wrong, because I must put there a ruler once to check all the error bars. So I'll use a different color for the line of worst fit. The line of worst fit is just drawn once if you have made the correct judgment, so you can always use a pen for the line of worst fit. It even helps you when you're finding the gradient to not make errors. So I can either draw the steepest line, which is from the top of the top error bar to the bottom of the bottom error bar, as long as all the error bars are being crossed. And that is very correct. It is easy. The top of the top error bar to the bottom of the bottom error bar is showing me that all the error bars are being crossed. You can see all the error bars are being crossed. And if all the error bars are being crossed, then I can just label this the line of worst fit. This is the line of worst fit. Okay, so I have to increase this now. I have joined the top. My aim was to join here, the top of the top error bar to the bottom of the bottom error bar, to the bottom of the bottom error bar. And you notice that all the vertical error bars are being crossed by this line. That is the steepest line. The shallowest line will be the bottom of the top error bar to the top of the bottom error bar. Let me try to draw the shallowest. I'll use green. So I have to fit this again on the page. I'm trying to draw for you the shallowest so that you can see it is less steeper. But the line is correct only if it goes through all the error bars. If it doesn't go through all the error bars, then you ignore that line. Okay, so when I try to draw the bottom and the top, it leaves out one error bar, which is the second last at the bottom, so I can't draw that line. Okay, so I'll just consider the steepest. The next thing is going to be, I think, to find the gradient. Remember to label your lines. Line of worst fit, line of best fit. I said you can draw the line of worst fit using a pen, because it is just you just put the ruler from the top of the top error bar to the bottom of the bottom error bar. If you see that all the error bars are crossed, you just draw the line. If they are not crossed, if one of them is not crossed, then you must make adjustments. You check the shallowest. If both of them leave out an error bar, then you must adjust the ruler so that it touches the error bar which is being left out. It should touch the error bar which is being left out. Okay. In one of the examples that I will do later on, I will demonstrate that. The next thing is to find a gradient. So I'm going to draw the triangle for the gradient. So let me use green for the triangle so that it is clear. I'm going to look for 2 points which allow me to draw one triangle for both lines. You may draw 2 triangles. I'm interested in drawing one triangle. For example, I'm taking these 2 points here. You may not take exactly the same points as mine because you are drawing on a paper, I'm drawing on a computer. Okay, then I have to look for 2 points at the bottom here, and I'm going to take these 2 points, this one and this one here. So that is my triangle for the gradient. I have this point here, I have this point here, and I have this point here and this point here. Okay, so let's find the gradient of the best fit. So I'll say gradient of the best fit equals to, I don't need to write much. I want best fit values. Y1 is, x1 is, I think this is 0.4, and x2 is, this is x2, which is 0.89. Then y2 is, this value here is 0.90591. So this is 0.91, I think, because if each box is 0.005 times 2, then we add this to 0.9, so that is 0.91. Okay, so y2 is 0.91, and what is y1? So for the best fit, y1 is this, which is also 1.31. So for the best fit, I have 1.31 minus 0.91 divided by, on the x-axis, I had 0.09, I mean 0.899 minus 0.44. 0.89 minus 0.40. I'm just writing them here so that I transfer them at once to the space required. Then for the worst fit x2 is 0. Let me see, it is this point here. 1, 2, 3, 4, 5, 6, 7, 0.87, and y2 is 0.91. I think I changed these ones. These ones are the gradient is negative, so this is wrong. It is 0.91 minus 1.31. x2 minus y2. I mean y2 minus y1. Then this one is 0.91 minus, worst fit is here, 1.31, that is 32. 1.32. On the x-axis, it is 0.87 minus 0.4. So this is 0.87 minus 0.4. So I'm going to transfer these to the other page. So gradient of best fit is 0.91 minus 1.31 divided by 0.89 minus 0.4. Then you have also to find the gradient of the worst fit, because they said include the absolute uncertainty. So you have to find the gradient of the worst fit, which is also 0.91 minus 1.32 divided by 0.87 minus 0.40. Okay. So the next thing is now just to press the calculator. I think the power of 10 is here on the x-axis, so I should add the power of 10 there. So let me bring the power of 10 here on the x-axis. So this is times 10 to the power of 10 of 4. This is times 10 to the power of 4. Okay. So I'm now just going to press my calculator. 0.91 minus 1.31 divided by 0.89 minus 0.4. Of course, remember there is times 10 to the power of 4 in the denominator, so it is going to be times 10 to the power of negative 4. So this becomes negative 0.816, negative 0.816. What is recurring is the whole figure, so I'll just say times 10 to the power of minus 4. Then here, it will also be times 10 to the power of minus 4. Let's check this. 0.91 minus 1.32 divided by 0.87 minus 0.4. So this is negative 0.87. Negative 0.87. I want three significant figures. 2. Okay, times 10 to the power of minus 4. So the gradient must be the best value, which is negative 0.816. Of course, I find the error first. So the uncertainty is of course going to be the difference between the two. So I'll just say maybe, because remember it is plus or minus, so whichever order you take, whether it's say negative 0.872 minus the other one, you just whatever order. So I'll say negative 0.816 minus negative 0.872. The answer is plus or minus. You can even first ignore the negatives, then you subtract the two values. This is times 10 to the power of negative 4. Okay, so I'll just say 0.872 minus 0.816, which is 0.056. 0.056 times 10 to the power of minus 4. So this is plus or minus. So here I will just say plus or minus 0.056 times 10 to the power of minus 4. Okay, that is the gradient with its uncertainty. Then the y-intercept, if it is required. So for the y-intercept, you must use the equation. Do not be tempted to read the y-intercept from the x-axis. If they have said do not include the absolute uncertainty, you don't find the y-intercept for the worst fit. So we are only finding the y-intercept for the best fit, which will be, I'm using y equals to mx plus c, making c the subject. So c is going to be the y value minus mx. I'm using just one pair of values from that we used for the gradient. So I'm going to use, let me look here. I'm going to use, let's say using these values here, 0.91 and 0.89. So the y value is 0.91 minus the gradient times the x value, which is 0.89 times 10 to the power of minus 4. So the gradient was negative 0.816 times the 10 to the power of minus 4. Sorry, this is power plus. The x value is 0.89 times 10 to the power of 4. The y value is 0.91. The gradient is 0.816 times 10 to the power of negative 4. Let me write it again so that it looks neat and better. So C for best fit is going to be 0.91 minus negative 0.816 times 10 to the power of minus 4 times the x value, which is 0.89 times 10 to the power of 4. So I said you choose just one pair of values from the graph. That is for the best value, of course, for the best fit. If they wanted the uncertainty, you would do the same for the worst fit and subtract. So just press the calculator here. I think this and this cancel out. So I have negative 0.816 times 0.89 then so that is the answer there. So I have 0.91 minus the answer, which becomes 1.636. 1.636. They have not asked for the units, so I will not find the units. Using your answer to A, C Roman 3 and C Roman 4, determine the values of R and I naught, include appropriate units. So this part here is what students always forget. Remember from the start we said the gradient, I think the gradient was negative T over R. What does that mean? This implies that R should be negative T divided by the gradient. They have not asked for the uncertainty here. So I'll just say negative 30.0 divided by the gradient. Our gradient was negative 0.816 times 10 to the power of minus 4. Okay, so we have 30 divided by the gradient, which is 0.816 exponent minus 4. So R is going to be 36,000, or just write 3. I'll write 368,000. Okay, 367,647. So approximately I'll write 367,000. Okay, or 3.67 times 10 to the power of 5. That is R. Then we know that the y-intercept was equal to, I think, ln of I naught times R. So y-intercept was equal to ln of I naught times R. This was the y-intercept. So it means if I remove the ln, if I remove ln, it means I naught times R is equal to E power the y-intercept. So it means I naught, I will divide both sides. So I naught is going to be E power of the y-intercept, which is 1.636, divided by R, which R is 367,647. Okay. So I'll say E power e power 1.636 divided by 367647. That's 1.397 times 10 to the power of minus 5. 1.397 times 10 to the power of minus 5. Of course, you can write the usual units of these quantities. R was resistance, so I could write 367,000. I could write ohms. I is current. I could write 1.40 times 10 to the power of minus 5. I can write this as amperes. But there are other units from the gradient. The R is T over gradient, and T is in seconds. The gradient was, on the y-axis, it was constant. On the x-axis, it was per farad. Was it per farad? On the x-axis, it was per farad. So this is per farad. R is equal to S over the gradient, which gradient was 1 over per farad. So 1 over per farad still becomes S per farad. So this is going to be S per farad. Then I was the y-intercept. I was equal to, no, I was not the I naught was not the y-intercept, but y-intercept is equal to ln of I naught r. Remember, e power this is a constant divided by r, where r has a gradient of, where r has the units of s per farad. So e to the power of the y-intercept. So I could have other units here as volts per ohm. You could have other units as R is S per farad, then volts. So that will be volts farad per second. You can derive the units. And lastly, this paper is still long. Determine the percentage uncertainty in R. So you just look at R. R equals negative T over the gradient. T has an uncertainty, gradient has an uncertainty. So the percentage in R should be the percentage in T plus the percentage in the gradient, which is simply going to be for T, this is absolute in T over T plus absolute in the gradient, divide by the gradient, then we multiply this by 100 to get a percentage. So the percentage in R is going to be 1 over 30 plus, for the gradient, the uncertainty was, I think, 0.0056 divided by 0.816. Of course, the negatives do not count, they just cancel out. The power of 10 also cancels out. That's why I'm not including it here. So I'll multiply this by 100 to make it percentage. So I'll say 1 divided by 30 plus 0.056 divided by 0.816. I'll ignore the power of 10. Then I multiply this by 100. The percentage uncertainty here is 10% or 10.2%. The experiment is repeated with the same value of T. Determine the combined capacitance C that gives a value of V of 1.2 volts. Okay, so that takes us back to the original equation, which was V equals to I naught times R e power negative T over CR. Okay, and remember we had that ln of V was equal to ln of I naught R minus T, it was T over R times 1 over C. And remember, this was the y-intercept and this was the gradient. So I could simply say ln of v is equal to the, no, ln of I naught r was the y-intercept. So this is equal to the y-intercept minus the gradient, sorry, plus the gradient, because the gradient is negative. So I'll say plus the gradient, which is negative, plus the gradient times 1 over c. So this means the gradient over c, when I get the gradient, divide by c, this is going to be ln of v minus the y-intercept. So now I can make substitutions, or I can say c is going to be the gradient divided by ln of v minus the y-intercept. So I will substitute. Remember, the gradient was negative 0.816 times 10 to the power of minus 4 divided by ln of v, which is ln of 1.2. The y-intercept was 1.3. The y-intercept is 1.636. 1.636. Okay, so I have to first check the denominator, ln of 1.2. Okay, so my answer would be positive. So minus 1.636. So the numerator is negative 0.816 exponent negative 4 divided by the answer. So it is 5.61 times 10 to the power of minus 5 farads. Okay, so when you follow this paper, you may not get exactly the same answers because you may plot a better graph than mine, but at least it gives you a picture of how you should follow through the steps. The steps are the same, the answers are going to be slightly different. In the case of any errors, you can always correct me. I have no problem with that. I'm not in any competition. I just record my lesson, my videos for students who are interested. So you can always correct me. I don't care even if you judge. So either in case there is anything which is not clear, you can always leave a message, write an email. I'm always willing to respond to the emails. Until next time, bye bye, and I love you.